So we've been developing a microscopic picture of an ideal gas, and we have some understanding of some of the basics of thermodynamics like temperature and pressure from a microscopic point of view. We know that temperature is the kinetic energy of the gas molecules, or related to the kinetic energy, and the pressure is the gas molecules colliding with the walls of the container. And so we can kind of understand the first law. We can understand, what the energy of the gas means, U. It's the kinetic energy of all the constituents. We understand heat flow might be from molecules which are moving faster colliding with molecules which are moving slower and transferring some energy, and so that's what we call heat flow. But what we don't yet understand is what's going on with the second law. So why do some things only happen one way? Why does heat only go from hot to cold and not the other way around? Why is it that gas will expand uniformly to fill up a container and not suddenly clump into one side? So what's going on microscopically with that? How do we understand that microscopically? To do that, we need to start doing a little more statistics and probability. So I'm going to introduce in this lecture these terms: microstate, macrostate, and multiplicity. So macrostate is the kind of overall big picture appearance of the system. It's like what it looks like from afar. Macrostate, that's kind of the sort of things we've been talking about so far in the course. The gas has a pressure, it has a temperature. That's its state, its macrostate. A microstate is the detailed microscopic arrangement of the constituents which give you that macrostate. So there might be many ways that I could achieve a certain pressure and a certain temperature of arranging the gas molecules in an ideal gas. So a microstate is sort of what's going on fine-grained in the microscopic picture. Macrostate is, what's going on in the big picture. And then multiplicity is the number of microstates which lead to the same overall appearance, or the same macrostate. So there might be many ways to achieve the same macrostate. And the number of ways that you can achieve the same macrostate is what we call the multiplicity. And eventually in this lecture we want to be able to calculate some multiplicities and probabilities using this technology called the binomial coefficient. So I'll go into that as well. So the quintessential example of the second law, or the increase of entropy, is this free expansion. I have the gas, I think I have 100 particles here trapped into one side. I remove the barrier and I see that after a short time, the gas is roughly spread out 50-50 between the two sides. And I never see the reverse thing happen. If I start with something 50-50 in between the two sides, I hardly ever, never see all of the gas suddenly clumped onto one side. And the question is, why is that? If you want to play around with this applet, there's a link posted here and also on D2L, where you can just Google PhET gas properties to reach this applet. So this is a complicated problem. I think I started with 100 molecules trapped in the left side. And that's a little more complicated than we'd like to start with. So as usual, start with a simpler problem. I'm going to start with just a few particles, a container with just a few particles. And we want to think about probabilities. How likely is it that I find all the gas particles in one side of the container? And how likely is it that I have, 2 on one side and 1 on the other side? So that's the question we want to get to. So let's start with a very small number of gas molecules. I'm going to start with 3. And I'm putting them in this container, and I've just drawn an imaginary line down the middle so they can move freely between the two sides. And let's assume that the gas molecules are distinguishable. Particles. So that means that I can tell them apart. I can sort of paint them different colors and tell which is which. And so I'll just label these particles 3 different labels. So I'll call A, B, and C. So that's particle A, particle B, particle C. And I can watch these 3 as time goes on. And now we're going to ask a question, which is, how likely is it that I find all 3 of those on the left side? And how likely is it that I have, in the configuration that I drew, where 2 are on the left and 1 is on the right? So again, let's talk about macrostates. So macrostate is like the overall big picture. And in this case, my macrostate is going to be the number of gas molecules on the left. So in the picture drawn above, it's in the macrostate 2, so there's 2 molecules on the left. And then a microstate is going to be the detailed arrangement. Whoops. Of molecules. And I'm going to use this notation. So I'm going to say above, I'm in the following microstate. I'm in the state A, B on the left, and then C is on the right. So I'm drawing that line to tell me which ones are on the left and which ones are on the right. So that's an example of a microstate leading to the macrostate 2 on the left, right? But there's other microstates which could lead to that same macrostate. So for example, this microstate also leads to the same macrostate. Okay. So those are 2 different microstates, AB on the left or AC on the left, but they both lead to the same macrostate, which is I have 2 molecules on the left. Okay. So now the question is, what's the probability that I end up with all 3 on the left? And we're going to make a fundamental assumption. So the fundamental assumption of statistical mechanics is all microstates in an isolated system, which this is, are equally likely. Okay, so please pay attention to this isolated system here. So this is a case where we're not thinking of, this system is totally not in contact with anything. It's insulated from the outside, and so then all microstates will be equally likely. But later on we'll talk about systems which are not isolated, and then all microstates won't be equally likely. So for now, this is a key word here, isolated system. Equally likely, meaning that it's equally likely for particle A to be on the left or on the right, and it's equally likely for particle B to be on the left or on the right. And another way of saying is that this one here with AB on the left is equally likely as AC to be on the left. So all of the different arrangements are equally likely, equally probable. But all of the different macrostates will not be equally probable because there might be more microstates leading to the same macrostate. So we'll do an example working this out. Before I work out an example, I'd like to give you a chance to think about it. So what's the probability that all 3 molecules are found on the left side when I look at the system? So here's a bunch of choices here. So why don't you spend some time, go ahead and pause the video, see if you can choose one of these options for which you think the answer will be. And then we'll work out a different example, and then once I've done that, I'll come back to this. So give yourself a minute or 2 to think about this one, which of these might be the right answer for the probability that all 3 are found on the left side if you look at the system. Okay, so I'm going to work out a slightly more complicated example, which is with 4, A, B, C, and D. So these are all distinguishable particles. So I labeled them all A, B, C, and D. And we're labeling the macrostate as the number of particles on the left. So you could have 0 on the left, 1, 2, 3, or 4 on the left. And the microstate is the detailed arrangement that I have. Multiplicity is the number of ways that I can arrange that. And then finally we'll get to the probability. Okay, so let's start working this out. Let's think about if I have 0 particles on the left, how can I do that? Well, I'm using this notation where I have the bar is denoting the boundary between the left and the right. So I have nothing on the left, and then I have all 4 of them on the right, A, B, C, and D. So there's only one way to have all of the particles on the right side, which is, of course, where they're all on the right side, A, B, C, and D. So there's one microstate, which leads to all 4 being on the right and 0 on the left. I'll leave the probability blank because we have to work the rest of them out before we can calculate that. Okay, how about one particle on the left? How can I achieve that? Well, there's 4 ways I can do it. I can have A on the left, I could have B on the left, I could have C on the left, or I could have D on the left. So let me write those possibilities out. Okay, so those are the 4 microstates. A on the left, B on the left, C on the left, D on the left. Each one of them leads to the same macrostate, which is one particle on the left. So we say the multiplicity is 4 here. There's 4 ways to achieve that. Now how about 2 on the left? There's a bunch of ways to do that. You have AB on the left, AC on the left, AD on the left. Try writing out all the possibilities. And so let me do that. Those are all the ways that you can pick 2 of those and put them on the left. So AB, AC, AD, BC, BD, CD. So there's 6 ways of doing that. Now how about if I've got 3 on the left? This is similar to the previous, or to this one, where I had 1 on the left, because I just have to single out one of them and put it on the right. So very similar to the macrostate when there's 1 on the left. So there's 4 ways of doing that. Let me just write those out. So there you go. I just singled out A, B, C, or D and put them on the right. The other 3 are on the left. There's 4 ways of doing that. And finally, I could have all 4 on the left, and of course there's only one way of doing that, which is having A, B, C, and D on the left, nothing on the right. So one way of doing that. So we've written down now all of the different macrostates and the associated microstates. Now the really, really important assumption is that all of these are equally likely, all these microstates. But the macrostates are not equally likely because a certain macrostate may have more ways of being achieved than others. So how do I figure out the probability? Let's add up all of the microstates. So I've got 1 plus 4 plus 6 plus 4 plus 1, that's 16. So usually we write this using this letter, omega total. That's the total number of microstates, 16, adding up the multiplicity of each one of those macrostates. If all of those are equally likely, then we can get the probability by taking the number of microstates divided by the total number of microstates. So this is going to be omega divided by omega total. And this is omega. So the probability that I have 0 particles on the left is 1. There's one way of doing that, 1 microstate, divided by 16 total microstates. And this one is 4 out of 16, which is 1/4. And this one is 6 out of 16, which is 3/8. And this one again is 4 out of 16, which is 1/4. And this is 1 out of 16. Okay. So you can see how likely it is to find the system in a particular state. And what you notice is that it's not impossible for all the particles to be on the left, right? It comes with a probability of 1/16. So it's not impossible, but it's more likely to find one of the particles on the left, and it's even more likely to find them evenly split, 2 and 2. Okay? So with this small number of particles, 4 of them, you see it's not impossible to have all the gas clumped on one side, but it's not very likely. It's 1 out of 6, probability 1 out of 16. So now that you know how to do this quantitatively, see if you can go back to this situation where there's only 3 and tell me what's the probability that all 3 of them are found on the left. What you should find is that it's more likely to find all 3 on the left if there's 3 balls than it is to find all 4 on the left if there's 4. And what you're sort of noticing the pattern is that the more atoms I have, the less likely it is to find all of them on one side. Okay? And that's the key point, right? Is that a gas has so many particles it was like 10 to the 23, that it's not impossible for all of them to be on one side, but the probability is so ridiculously low that if you waited the entire age of the universe and watched it every second, you would never see this thing happen. So it's not impossible, these things that are irreversible, it's not impossible for heat to go from cold to hot, but it's so ridiculously unlikely that we never see it in our observations. Okay? So it's not prohibited, but it's prohibited by probability, that it's so ridiculously unlikely that it never occurs. That's the key point.